lab 32 is that in your parts kit you got a transformer, a fuse, and a power cord. So what we need to do is we need to build up our transformer, and so we're going to be coming out of our plug, and it's going to be plugging into our 120 volts. And then that's going to go into our transformer. So on this side we're going to have 120 volts AC. Then our output of our transformer with our center tap. So typically you'll have two colors of the same and then one odd one out. The odd one out is going to be your center tap transformer. And then coming out of our, so we're going to just do a full wave bridge rectifier with a center tap. So that's your typical diagram for your load, our load. So that's your typical diagram for a center tap full wave bridge or a full wave rectifier with a center tap. Our transformers are only capable of handling 1 amp on the secondary side. And so if you're going to, because now since we're working with higher voltages, and this thing can, our outlet can produce as much current as we want to give it for the most part, up to about 15 amps, we need to make sure that we protect our transformer and our circuit from overcurrent. So if you accidentally ended up shorting out your load or something like that, it's going to try and get in as much current as possible. So we have to protect it. When you're working with a full wave center tap transformer, these two leads are actually hot. And then this one's really considered hot too, but since we made this as our reference point to the ground, this is going to be our plus or minus 0 volt. So if you're going to protect a circuit that was in our, using our center tap, what you would end up having to do is you would have to protect your fuses on both legs. You'd have to use 2 fuses. And then each one of these fuses would have to be rated at 1 amp. And then that would protect your fuse and your transformer. So remember, as our signal's coming in, we're going to have a full wave. It's going to be going positive, and then it's going to be going negative for our second alteration. So when we're doing our first alteration, 1 half of our circuit's going to be working, and the other one's going to be rejecting the negative side going on. And it's going to kind of flip-flop back and forth. So you have to protect both sides of the leg. And that would protect your circuit from 1 amp of current. Well, if you don't want to use 2 fuses, what we can do is, since we only have 2 leads going in, and typically they're your black leads, this is going to be your primary side, and that's going to be your black leads. What you can do is you can eliminate these fuses here and protect your circuit on the primary side. So assuming that we had a 10-to-1 ratio, let's see, so 10-to-1, yeah, that would be correct. So we have a a 10-to-1 ratio on our transformer, approximately, just approximately. If I had 120 volts on my primary side, what would be my voltage on the secondary side? Yeah, 12 volts approximately. And on our transformers, it's actually 12.6, but just to keep our numbers nice and simple, we'll just keep it as 12 volts. But if we actually end up on our transformers, we end up getting 12.6 volts, and we actually end up getting a little bit more than that. So if we drop down from 120 volts to 12 volts, then what's my current going to be on this side? So this is going to be 12 volts with a capability of a maximum of 1 amp. What would be my maximum current that I could have on my primary side?
10 amps.
No.
100 milliamps.
100 milliamps. Yep, because remember, whatever we lose in voltage going over to our secondary, we gain in current. And then whatever we gain in current, we lose on this side. The power always has to equal. So if our voltage is going down on our secondary, that means we have a more current capability on our secondary. Then it's just the opposite here. If I have more voltage on my primary, I'm going to have less current on my primary, because the power has to equal between the two. So on this one here, then, what we do, instead of fusing it with a 1 amp to protect our circuit, we're going to be protecting it with a 100 milliamp fuse. Okay? So typically we always kind of protect our primary side. Eliminates us having to put in 2 different fuses onto our secondary, because we can have multiple taps, and some of the taps, we can have up to 15, 20 taps, depending on your circuit that you're doing and stuff. So a lot of times you can have multiple taps. So this 100 milliamps will never make sure that the current going through our secondary will ever exceed our 1 amp. Now 100 milliamp fuse isn't very much, so it doesn't take much to short out your load or put in the wrong resistor, start drawing 1 amp of current on my secondary, and to blow that fuse of the 100 on the primary of the 100 milliamps. So you have to be a little careful about when you're working with your circuits there. It's very easy to blow that 100 milliamp circuit, so double check your circuit before you plug in your power going into there. So when you're wiring this thing up, you're gonna, and I got some shrink wrap and stuff like that. So what you're gonna do is you're gonna get your little fuse holder here that's already all in one piece. What you're gonna do is just take your wire cutters, cut your wires in half, strip them down, and then you're gonna have to solder that fuse in series with your primary. And then after that, once you do that, then you're gonna hook up your power cord going up to your fuse, and then the other one gets wired up directly up to the primary wire. So what I typically do is I'll strip this one back a little bit. So what I kind of do is I take half my wire length so that all my wires are still the same length. I kind of cut my wires back. I leave one cord as the full length, and then cut this one back a little bit so that way I don't have any big loops on my thing. Kind of get that so it's so it's somewhat even and stuff. Cut back that one wire so it's somewhat so they end up being equal once you start hooking up to your transformer. All right. Then the other thing is that typically when we're fusing our fuses, we want to fuse our hot wire. So when you're working with 120 volts AC, you're going to have a hot wire and then a neutral wire. So we want to make sure that we're fused on the hot wire side. Now to determine which one is your hot wire, on your plug there's going to be one that has a little flat, this little fatter blade on it, and the other one's going to be a little narrower. The one with the neutral is going to be the bigger blade. That's going to be your neutral. So the other one is going to be your hot. So if you want, so all you have to do is just take your ohm meter, flip your ohm meter onto the fatter blade one, and then find out which one's your neutral, and then you can. The other one is obviously going to be your hot, then the other one will be the hot. So you want to make sure you hook it up to the hot. It would work either way. It still would protect the circuit whether it's on the hot or the neutral. But if we're tying our neutral, this one here, our neutral side, could very well possibly be getting tied down to our chassis of our circuit. So, for example, it might be tied to the computer case or something like that to help us protect us from any electrical shock and stuff like that. So we always typically fuse the hot side of our wires there. Okay, so that's going to be our first step, so that we can start doing lab 32 with our transformer. So just be careful when you're working with 120 volts AC. That's enough to hurt you. So be careful of it. Don't be touching. Don't be monkeying around with it. We've been all the way up until this point. We've been working with low voltages, low currents. Nothing could hurt us. But now we're actually working with higher voltages, with the higher capabilities of higher current stuff. So make sure that you don't have any exposed wires on especially on your primary side. If you never did any soldering before or anything like that, I can help you out when we get into the lab there. I'll kind of help you out, get you going on that. And then if you've never worked with string tubing, I'll help you with that. But I'll get a bunch of chunks of string tubing cut up here today and get those ready for you. So that's going to be our first step, is that we're going to have to get our transformer built up so that we can work with our circuits. All right, then on our secondary side. So on mine, I got the 2 red wires and a white wire. So my 2 red wires are going to be my 2 outer ones. That's where I'm going to measure my 12.6 volts. You're going to probably find out that it's probably closer to 14 or 15 volts without a load on there. But the minute you hook up a load to it, that voltage is going to drop quite a bit really quick. So without a load on there, that transformer really kind of producing some phantom voltages and stuff like that. So it really actually shows a lot higher than what you expect. But the minute you kind of put down a load on that, it really loads down that transformer down until it gets down to about that 12.6 volts. Then it starts maintaining the current and stuff like that and the voltage. So and then in your kit there, you should have gotten some female banana jacks. And you should have gotten 2 red ones and a black one. And these are just receptacles for our banana jacks. And so you're going to be hooking up those banana jacks fuses.
Kurt,
yeah.
Before you go further, can I ask a question?
Sure.
Talking about this neutral and then hot.
Yep.
Can we also, is there a way that we can also know which one of these black connect the hot to?
What's that?
Which one of these black wires from the primary side to connect the hot line to?
Yep.
Is there a way to identify?
On the transformer itself?
Because we want to connect.
Yep, the transformer itself you don't have to worry about.
You can connect it to any
one of the 2 black wires. Yep. That one won't really matter. Yep, either one can be, good question, yeah. So either one can be hooked up to so either 2 black wires can be hooked up to the hot or to the neutral.
Just make sure your fuse
It's just coming out of your plug that it's going to be critical.
Okay.
Yep. Yep, good question though. All right, so then on your secondary side, then is where you're going to put your banana receptacle here, and these ones will be our 2 red ones, and then the other one then is going to be our black one. And so you're going to have it. So now that we can, so what you're going to end up doing is you're going to just come out of your receptacles, put in a banana jack, and then you can go ahead and come out with a test lead coming out of your proto board and stuff. Just come out, you can plug in your banana jack into it, and then put on your alligator clips and clip onto a couple of test leads going into your circuit there. So these will just be kind of our little banana jacks there. This will be your flat. So then we want to make sure that every one of them has a little shield onto it. So you want to make sure you get those, put those little shields, those little insulator covers. Make sure you slide those onto your wires before you solder onto your receptacle. Otherwise, once you get your receptacle soldered on there, you're not going to be able to slide your shield on there. So make sure you slide on your insulator first, solder on your receptacle, and then slide that back over. Make sure that there's nothing exposed, because when this thing's sitting loosely on your workbench and stuff, we don't want either the red or the black to touch together or the two reds to touch together, because that will end up creating a short and it'll pop your 100 milliamp fuse pretty quickly. So make sure you slide on your insulators. Slide on your insulators first onto your transformer wires. Okay, and then that'll give you just like a little female jacks, just like you would see on your power supplies. Then you can come out with your banana jacks and your banana leads and stuff like that, and clip onto your circuit there. Yeah, with just an alligator clip, I'm just showing it that you have the banana lead there, and yep. Okay. Yep. So yeah, we need to have just little solder cups and stuff, and these things, the wires already are tanned and stuff, so you should be able to, and I would trim down my wire leads a little bit if they're sticking out too far. Mine are cut, but if they're stripped out really long and you got a lot of exposed wire, come down just a little bit so that you don't have much exposed wire, just enough to get your solder in there. And then that way the rest of the insulator will protect where the solder cup is. So that's going to be your first step before you even start working on Lab 32, is to get your transformer built up and get that ready to go for your lab, and that one will be used for the rest of your lab then. All right, any questions on that? It's pretty straightforward. Okay. Yeah. So that'll give us our power supply going into our rectified circuit. All right, then let's take a look at Lab 32 on page 268 there. I am trying to kind of go through this a little bit quick because I do want to get us into lab. We got to get going on our lab, but still need. I've only checked up just a couple of Lab 31, so make sure you get your Lab 31 checked off here today. We haven't had much lab time, so I want to make sure that we kind of get going on our lab so we can get moving along with our cover the rest of the material that we need to get put over here. Oh, did you really? Way too big or way too small? Way too big? Oh, sure, and that's why you're getting the voltage drop across your line. You're right. No, but I did. At least I figured it out. Yeah, because you were actually measuring your leakage voltage across your diode. That was your leakage current. All right, so you'll be building up, the full wave center tap rectifier. You'll be building up the bridge rectifier, and then after you get built up all your circuits there, then what we're going to do is we're going to hook up what we call a regulator. All right, so there's our full wave bridge rectifier, and then it has our filter capacitance, and that's what decreases our ripple, and then our load. So when we're kind of looking at the circuit here, we know that we have 120 volts AC going in, and this thing is going to be going both positive and negative. And it's going to be at 120 volts AC. Then we're going to be coming out of our transformer at approximately 12.6 volts AC out of our secondaries, and that one's going to be also going positive, negative. Then after our transformer, that's where we go into our rectifier, and coming out of our rectifier, then that's where we get our pulsating DCs with a lot of ripple. And then with our filter in there, then it kind of starts filtering out some of that ripple. Remember that capacitor is going to charge and discharge, and it's going to put back into the circuit. When my ripple starts to drop really low, then my capacitor is going to decrease that ripple. And so then coming after my filter, then my ripple becomes a lot, and it might be at we'll just say, let's say approximately, 14 volts. About 14 volts DC, we'll just say. Okay, it's going to have a DC offset, but it's still going to have a little bit of ripple. And the ripple, remember, is just the amplitude of what it is from the lowest peak to the highest peak. And it's just an amplitude. It's not relative to where it is sitting on the DC level or anything like that. But we're trying to get, we're getting kind of going to where we're getting a nice DC level line. We want one as smooth as can be. When we want 14 volts DC, we want it to be as smooth as can be. We don't want a lot of ripple. So even though the filter cap will take care of a lot of the ripple, take it from a pulsating DC, give us a slight ripple with a DC offset. But a lot of times we want it even a little bit even cleaner. And then that's where we hook up what we call our regulator. And this regulator will end up coming out of the output, will end up almost giving us a nice flat, clean DC voltage. It'll make it a nice straight line. The regulator itself is an integrated circuit. It's just like our op amp. There's a whole bunch of other circuitry that's inside this regulator that helps us maintain that DC voltage. And it actually oscillates at a very high frequency. And so if you really zoomed in on that DC level, and if you really zoomed in on it, if I zoomed in on it, you would see that the frequency is, and it's going to be kind of at a real high frequency, kind of jumping around all over the place. But you really have to zoom in on it to see what's watching that regulator actually work and stuff. But it's happening at a very high frequency. It's oscillating it, and it's really maintaining that ripple. So it really decreases our ripple. So the regulator will actually maintain it. And if I, for example, in their book here, they have a 7812. This regulator that's in the book is a 12-volt regulator. So if I put enough voltage into my regulator, I always have to make sure that I have more than what the regulator, whatever the regulator voltage is. So if this is a 12-volt regulator, I have to have more than enough voltage going into that regulator so that it can maintain that ripple. My ripple can never drop below that 12 volts, otherwise my regulator cannot regulate that voltage. If it drops below the 12 volts going into the regulator, it can't maintain that 12 volts. It always has to be higher voltage than what the regulator is. And you can run it all the way up to, 36 volts or whatever. You can really, put in a lot of voltage into this regulator. And coming out of the regulator is always going to be our 12 volts DC, and it's going to be a nice clean DC level. Without that regulator, if I have that regulator, if I just have my bridge rectifier with a filter cap, if I change my load, remember that capacitor is going to charge and discharge going across that resistor. If I have a very large load across that capacitor is going to discharge at a higher rate and stuff, and it's going to create a lot larger ripple. If I put in a smaller load, one with less resistance, then the filter cap has no problem kind of maintaining it. It still has a little bit of ripple, but not a lot of ripple. If I use a regulator to do this and maintain my regulation, no matter what I do to the load, it's still going to maintain a certain amount of DC voltage going into that regulator, or coming out of that regulator. It's still going to have a very small amount of ripple. Like I said, it's very small. You really have to zoom in on it. But it'll maintain it no matter what I do to the load. Unless I exceed the current of whatever my regulator is. So the regulators are used quite a bit. We always are kind of using our regulators and stuff to maintain a nice DC level and also to keep our regulation so that if I put in a 12-volt regulator, it's going to be at 12 volts or something close, very close to it. Now in our and then there is a small cap, this bigger cap. This is this one right here, the one that's coming out of our bridge rectifier. This cap is for filtering out so that we get some of the ripple out of there. So we're not just getting our DC pulsing, and that we're bringing in, reducing our ripple by quite a bit. That's put into our regulator. Then outside the regulator is a very small capacitor, 0.01 microfarad capacitor that's on the output of our regulator. That one there is just used to help stabilize this oscillation that the regulator is doing. So we want to be kind of keep an eye on that, making sure that we have that small capacitor in there just to maintain the oscillation so it doesn't go in a runaway condition. So it just kind of stabilizes out the oscillation of that regulator. Okay, so we come in, We have alternating current on our primary side, alternating current on our secondary side. We go through our rectifier. We end up putting it into a DC pulsating thing. We go into our filter. We filter out some of the ripple. Then we go into our regulator, and then we maintain a nice constant DC voltage. And then, like I said, there's a big section in our book about regulators. Make sure you read that. So I'm going to kind of have you guys kind of get into your research mode, kind of figure out how to research it. How do I hook something up? I'll kind of give you some hints of some things that you have to watch out for. So the 12 volt one and the 7805, which is 5 volt one, those are some of our more common regulators. But the one that I always, in my parts kit, I always have what I call the LM317 regulator. That is a variable regulator. That means I can set up this one to be any voltage from 1.2 volts all the way up to I think it's like 36 volts or something like that, but I can vary it to any voltage. So now what I can do, I can vary my voltage. I can make it a variable regulator by hooking up a potentiometer up to it, and I can have a variable power supply. Now I've just converted this into a variable power supply, and I can get, from this one I can get 1.2 volts up to whatever my maximum voltage is that I'm putting into that regulator. If I'm only putting in 12 volts into that regulator, I'm not going to get anything more than 12 volts. I'll probably in fact get a little bit less than 12 volts coming out of my regulator for the capable voltage coming out of there. Because this regulator itself is a solid state device, then it's going to drop some of the voltage going across that regulator. So I always have to make sure that if I need something, if I want 12 volts, if I want to have a range from 1.2 volts to 12 volts, I have to make sure at least I would give myself something like about 15 volts going into that regulator. So you always have to make sure that you have enough voltage going into that regulator to maintain the voltage that you want out. So that's our LM317, and that's in the book also. They kind of talk about how to wire that up, how to wire up the LM317. And the case that we're using is the TO92 case. It's going to look like a lot of our other transistors. You're going to have other components that are going to look this shape. These cases are just standard cases. They could either be transistors or FETs, MOSFETs, any other type of devices, and they all get put in the same case. So you have to make sure you read what the number is on there. And ours should have on ours it's going to be this style, and it should say LM317. Okay. So one thing what you're going to want to do, your first thing that you're going to want to do when you get down to your further investigation is that you're going to want to print out the data sheet for the LM317. These pinout numbers are for the 7812. You have to verify to make sure that you know what the pinouts are. So here we have the input, that's going to be on this side. Here's our input going into our regulator, and then we're going to have our output going out of our regulator, and then we're going to have and then there's going to be the third one that's going to be our ground. Where are they showing the ground?
Down at the bottom.
Yeah, they don't see coming out of the I don't see it coming out of the.
They don't show it coming out.
They don't show it coming out. But then the third one is going to be going to your ground there. Okay. So make sure that make sure you watch out for the pin numbers. Take a look at your data sheet. You should have your data sheet. All you need to do is print out that first data sheet. You should have that printed out when it comes time for me to come and check it out. Show me that you did print out that data sheet for the LM317. Identify what the pinouts are. Make sure you know where your output, ground, and input is. Make sure you know where those pinouts are. Don't assume anything about, don't assume that this is pin 1, pin 2, pin 3. Make sure you look at your data sheet on how to figure that out. So instead of using the 7812 on your further investigation, use the LM317. And you're going to have to read about it, because since it is a variable, going to be a variable regulator, there's going to be a voltage divider in there. That's going to be going up the output of our LM317. And then that variable potentiometer in there, that's what gives us our voltage range. And there's always a certain value resistor that we always use. So this is right in our book here. So on page 750 is where it's showing the regulator. All right, so you can see here's the one that I was telling you about. There's always this one here that's R1. This is always going to be a constant 240 ohm resistor, okay? You're probably not going to find that in your parts kit. So either you have to do one or two things. You either have to combine a couple of different resistors to get that 240 ohm resistor, or just put in another potentiometer, okay? And set it up for, put another potentiometer wired up in the rheostat, and adjust it so that you set it for your 240 ohms. You have a potentiometer here, and then R2 is going to be your variable potentiometer. R2 is the one that determines whether that voltage is going to be going up or down. And it's based on a voltage divider formula that's being fed back into it. So kind of the feedback going into the LM317. So you're going to need two potentiometers. One to set up R1 for your 240 ohm resistor, which is always the standard for the LM317. And then your R2 at 1 kilo ohm, that's going to give you your variable output coming out of your circuit. Okay? So that's going to be your further investigation. And then run through the range. Tell me what you can get for your minimum voltage, what can you get for your maximum voltage using our 12.6 volts AC transformer. Okay? And so there's a whole section of understanding how that LM317 works. I want you to kind of start doing some investigation, start reading up, so that if all of a sudden you wanted to make up your own variable power supply, how would I go about creating one? Can I go ahead and build this circuit up on my own by just looking at the data sheets and the textbooks or manuals, whatever I have, it's accessible to me to go ahead and build that up. All right, and you can kind of see here's we don't have the switch, but here's our switch going into our primary, and then here's our 0.1 amp fuse to give us our 1 amp on our secondary. So it's kind of our, in your further investigation, it's going to look very similar to this, except we're just going to plug in we're not going to wire in the switch, we're just going to plug it in or out into our outlet. But this is going to be there's your circuit right there for your further investigation. So more than enough information for you to get your further investigation up and running.
So you are supposed to use the
Yep. I can't remember what came in your parts kit, but yeah, it should be I think you did get the 4001. Yeah, use the 4001. Yeah, diodes. Yeah. All right. Yeah. So the big thing too is just kind of understand what kind of signals I have from each step. What am I looking at? So when I'm probing around, take a look at the different stages of your power supply. Here I got 120 volts AC. Just assume that we have 120 volts AC. Don't hook up your oscilloscope up to your 120 volts AC because some of the oscilloscopes can't handle that high voltage. They're typically for lower voltage signals and stuff like that. But coming out of your secondary, you should be able to measure that voltage and see the AC waveform. Then measure it coming out of your rectifier without the cap on there. And you should be able to see that DC pulsating signal going in there. Put the cap in there, and you should be able to see the ripple, and you should make sure that you're on your DC offset so you can see that offset being generated and still being able to see the ripple on there. Then hook up your regulator, or even with regulator in there, you'll see your ripple going in, but you'll see hardly any of your ripple going out. Okay, so take a look at when you're probing around. Take a look at the different signals of what we're getting through each different stage of that thing. This one here is the hardest one. If you want to see this, you got to make sure you physically remove that capacitor in there. Because if I'm going across here, even though it doesn't look like I'm going across my my capacitor, I really actually am, because it doesn't matter if my ground is here or here. I'm going across that capacitor, so I'm going to automatically get that. So you physically have to remove that capacitor out of there to see that large amount of ripple. So now measuring your secondary of your transformer. What do I need to do though to measure my voltage across my secondary using my oscilloscope? So here's my secondary. My grounds are here. I'm not measuring it, referencing it to my ground. I'm measuring it from my two hot wires coming out of my secondary. What do I need to do to make sure I'm measuring my voltage properly with my oscilloscope? What do I need to set up my oscilloscope? How do I need to set up my oscilloscope for that? Yeah, you're going to take your channel 1, put it onto here, take your channel 2, put it onto here, and then you're going to still use your ground clip. That one's going to go onto your ground, because the ground clip always has to go on your ground, and then you're going to just take your channel 1, subtract your channel 2, and that'll give you your voltage of your secondary. And you're going to take the difference between those two signals, and you'll see your voltage of your secondary. Like I said, without a load on there, it's probably going to read about 14 volts AC. With a load on there, it'll get closer down to the 12.6 volts AC. But when you start putting the load on there, that voltage across the secondary will start to drop. So be careful of that when you're doing your measurements across your secondaries. Don't float the ground. If I ended up putting my ground on one of my secondary leads, I'm going to short out one half. I'm going to short out my bridge rectifier, which I'm going to short out my secondary winding, which is going to draw more than 1 amp of current, which in turn then is going to draw more than 100 milliamps of current on my primary and pop my fuse. And there's nothing worse than to have to come walking up to me and ask me for another 100 milliamp fuse. Especially when you're second semester students now. So be careful of that. Be very careful about. Try avoiding not to pop that fuse. Use all your kind of take your time. Be careful of that. All right. So more than enough information for you to do that lab. So all we have, this is only our second lab. We're already into our 4th week already. So I still need to see lab 31, and I want to get through lab 32 here this week. Okay.
Can we use an IDAC?
So I think, let's see, since we're, well, you can use a MindAct, yeah, you can use a MindAct for your oscilloscopes and stuff like that and stuff. You can use your breadboard on your MindAct and stuff like that. You're just gonna have to hook this up to your breadboard on the MindAct and stuff. Yep. But just remember, you know, it's good to use both pieces of equipment, both use the MindAct, the oscilloscope, and then the other one. So we'll push off the quiz. We'll push off this quiz to the 14th, and then let's see. So that'll be the 14th, and then the iClicker will be on the 10th. So we'll do the iClicker next Monday, right before, and then we're going to start doing Zeners on Monday. We'll do the iClicker before our lecture, and then on the 14th will be the quiz on power supplies. Yep. Now I'll get back to your quizzes. I didn't get time to get your quizzes graded here over the weekend here, but I'll get those on to you on Wednesday here. I'll get those quizzes from that we did on Friday. I'll get those actually on Wednesday here. And those out. All right. Any questions? If not, let's get going on our labs. Let's get done with labs 31 and 32.